Hello everyone. Today I am pleased to present our work, C4D, 4D, made from 3D through dual correspondences. The structure of my presentation is as follows. I will begin with the introduction and motivation for our research. This will be followed by a detailed explanation of our proposed method. Subsequently, I will present our experimental validation and results. Finally, I will conclude with a summary of our contributions. State-of-the-art point map-based 3D reconstruction methods, such as Duster, have demonstrated remarkable success in static scene reconstruction. However, when applied directly to dynamic scenes, they exhibit significant performance degradation. This is because moving objects violate the multi-view geometric constraints upon which these methods are built. While some works like Monster address dynamic scenes, they typically require fine-tuning on specialized 4D datasets, which are often difficult to acquire. This motivated us to develop a more flexible, plug-and-play framework. Our objective is to upgrade existing 3D reconstruction models for 4D tasks without the need for retraining on 4D data. The primary challenge in extending 3D reconstruction to 4D lies in effectively incorporating the temporal dimension. Our central hypothesis is that temporal information can be robustly captured by leveraging two distinct types of temporal correspondences. Specifically, we utilize short-term, dense correspondences derived from optical flow, and long-term, sparse correspondences obtained from point tracking. By integrating these dual correspondences, we can not only accurately segment dynamic regions from the static background, but also incorporate temporal smoothness constraints into the optimization process, leading to a more consistent and coherent 4D reconstruction. This slide provides a schematic overview of our C4D framework. Given a monocular video input, the process begins with the construction of a sparse scene graph. For each pair of frames in the graph, we perform three operations in parallel. We employ a pre-trained 3D model, such as Duster, to predict pairwise point maps. We use an off-the-shelf estimator for optical flow, and we utilize our novel dynamic-aware point tracker, aka DIN-PT, to generate long-term 2D trajectories. The correspondences from optical flow and DIN-PT are then used to estimate motion masks, which isolate dynamic scene elements. Finally, all intermediate outputs, point maps, flow, tracks, and masks are fed into a unified, correspondence-aided optimization process. This process jointly optimizes all variables to yield the final 4D representation, including per-frame point maps, camera intrinsics and poses, and 3D point trajectories. Let us now examine two core components of our method in greater detail. On the left is the architecture of our dynamic-aware point tracker, DIN-PT. A key distinction from existing trackers is that DIN-PT additionally predicts a mobility attribute for each point. This capability is critical for disambiguating object motion from camera-induced motion in the world coordinate frame. The process for motion mask estimation is depicted on the right. We leverage the static points identified by DIN-PT to robustly estimate the fundamental matrix between frames, as these points are only affected by ego motion. We then compute the epipolar error across the entire image. Regions with high error, which violate this ego motion constraint, are consequently identified as dynamic, allowing for accurate mask estimation. Our correspondence-aided optimization is guided by four distinct objectives. First, the global alignment objective, adopted from Duster, ensures the overall geometric consistency of the reconstructed scene. Second, the camera movement alignment objective aligns the estimated camera ego motion with the optical flow field within static regions of the scene. Third, the camera trajectory smoothness objective penalizes abrupt changes in camera pose to enforce a temporally smooth camera path. And finally, our proposed point trajectory smoothness objective lifts 2D tracks to 3D and minimizes their temporal deviations, ensuring temporally coherent 4D reconstructions. We now turn to the experiments part. These tables present the results for camera pose estimation and video depth estimation on several benchmark datasets. We applied our C4D optimization framework to 3 different pre-trained 3D models and compared it against the standard global alignment baseline. The results consistently demonstrate that our 4D formulation yields substantial performance improvements across all base 3D models and datasets. The visualizations on the right display several examples of our 4D reconstructions. To complement our quantitative findings, we present qualitative comparisons. On the left, we compare our generated motion masks against those from Monster. Our method produces masks that are visibly more accurate and complete, which is crucial for the subsequent optimization stages. On the right, we illustrate the effect of our point trajectory smoothness objective. The temporal depth visualization at the left confirms that our full pipeline produces more stable and temporally consistent depth maps. Furthermore, the 3D trajectories at the right show a clear reduction in temporal jitter after applying the PTS objective, resulting in smoother motion paths. In conclusion, our contributions are fourfold. First, we introduced C4D, a framework that upgrades 3D reconstruction to 4D by incorporating dual temporal correspondences. Second, we proposed a dynamic aware point tracker, DIN-PT, capable of predicting point mobility in world coordinates. Third, we presented a robust motion mask prediction mechanism guided by these correspondences. And fourth, we introduced a suite of correspondence-aided optimization techniques that improve the consistency and smoothness of 4D reconstruction. Our comprehensive experiments demonstrate that C4D effectively reconstructs dynamic scenes and achieves highly competitive performance on multiple downstream tasks. That's all. Thank you for your attention.